Hello everybody. Today what we're going to be looking at is lesson 2.1e, examining linear growth. So what we want to do is define the characteristics of a proportional relationship in non-proportional linear relationships. We're going to provide some examples here. Alright, so let's start with proportional. Definition, there's three things that we can focus on, is when the table has a constant of proportionality, and then its graph is linear and goes through the origin. And then the last one is the equation only has a, does not have a constant. Equation does not have a constant. So examples from that is if we looked at a table like x and y, we have x and y, and if I had numbers like 0, 0, 1, 4, 2, 8, 3, 12, and I looked at the ratio of the numbers that do not have 0 in the denominator, such as 4 over 1, 8 over 2, 12 over 3, we would say all of these simplify to 3, so it, all of those simplify to 4, so it does have a constant of proportionality. The next one would be the table. It's a linear graph, and it goes through the origin. And the last example would be if we looked at the equations, we'd have something like y equals 2x, or y equals 3x plus 1x, or y equals 7x plus 0, or y equals 1 over x. Something like that, where there's no adding or subtraction of a constant once it is simplified. So I provided some tricky examples here like the plus 1x and plus 0. Now let's look at non-proportional. There are a handful of things that makes it non-proportional. First thing is the table values. I should say the ratio of y over x are not all equal. The next one is if I look at the graph. So the graph may be linear, but it does not go through the origin. And the final one is the equation does have a constant. That just means we're adding or subtracting a number that does have a variable. Okay, oops, sorry. Plug it in my iPad. Let's go ahead and look at these examples. So the first example is of a non-proportional table. If I have x and y, let's say I start at 1, 3, 2, 5, 3, 7, 4, 9. As we look at these numbers, we see it does have a rate of change. I am increasing by 2 each time, but the ratio, 3 over 1, 5 over 2, 7 over 3, does not all equal the same number. Therefore, there is no constant of proportionality. Second one is the graph. It could be a straight linear line, but it does not go through the origin. All right, my pen ran out of battery. Oh wait, did it run out of battery? I thought my pen ran out of battery. It did not. So let me go ahead and show this one more time. Here we go. And then the next one, the equation would look like something like y equals 2x plus 7, or it might look like y equals 3x minus 4, or y equals 1/2 x plus 2. This plus 7 minus 4 plus 2 is what makes it non-proportional. So now we're going to look at some word problems here, and we're going to fill out the table and graph and state all of stuff. So it says Jack is filling up an empty swimming pool with water. The pool is being filled at a constant rate at 4 gallons per minute. So state the independent variable. Well, anytime time is involved, it's usually going to be the independent variable. And what is dependent on time is the amount of water in the pool, where x is time and y is gallons. Alright, well, let's complete the table values. So it's at 4 gallons per minute, which means at 2 minutes there's 8, 3 minutes there's 12, and 4 minutes there's 16 gallons. Now it says state the rate of change. Rate of change is not the ratio of 8 over 2 or 12 over 3. It's how much am I increasing by? Remember the increase of y over the increase of x. So what am I increasing by? Well, I'm increasing by 4 to go from 8 to 12 and from 12 to 16. And then for time, I'm increasing by 1 minute each time. So this would look like 4 over 1, and then once again 4 over 1, and all of these reduced to is just 4. Now what does this represent? It represents the 4 gallons per 1 minute. Now it says, is this relationship proportional? Use the context to justify. And if we looked at 8 over 2, 12 over 3, and 16 over 4, all of these reduce to 4. Now it says the context. That means use the word problem. And what do we know about this pool? At 0 minutes, this pool was empty. So the pool started off empty. Now it says make a graph of the data, label the x and y axes. Well, like we said, x is our horizontal one going left and right, while y-axis is our vertical. And this would be time, and this would be gallons. So at 0 minutes, there's 0 gallons. At 1 minute, there's 4 gallons. 2, there was 8. 3, there was 12. 4, there was 16. Now we need to decide, is this discrete or continuous? And in this example, it's actually a continuous graph, because we can have, at 1 minute we can figure it out, at 1.5 minutes we can figure out how much water, at 30 seconds, at 2 minutes and 20 seconds. The water is continually filling up the pool, okay? So we can have a fraction amount of water in the pool. So we already answered this. We'll have a continuous graph. And the reason because we can have a fraction amount of water. Now state the coordinate of the y-intercept. The y-intercept is where does this graph cross the y-axis. And right here it's 0, 0. And what that means is at 0 minutes, there was 0 gallons in the pool. All right, now what we're going to do is define our variables and write an equation. So I want to write this in words first. The total amount of water total gallons equaled 4 gallons per minute. Okay, so what this would say is then the total amount of water is equal to 4 gallons per minute, where Y is the total water, total gallons, and X is the minutes. Explain how you know the situation is linear by using the context. Well, it's linear because it has a constant rate of change. In this instance, the constant rate of change was 4 gallons per minute. Now it says, how would we change the context of the relationship between number of minutes and the number of gallons if it's modeled as y equals 4x plus 2? Well, the original one we came up with was y equals 4x. So what's the difference with y equals 4x and y equals 4x plus 2? And as I'm sure we can notice, it's that plus 2. Now, if we're talking about water in the pool, this is saying, well, when we showed up, there was already 2 gallons. So the pool already had 2 gallons before I started to fill it up. Okay, next one. Now it's saying you are visiting New York City and a taxi company charges you $25 per hour. So wherever you go, the taxi company is just going to charge you $25 per hour. It says state the rate of change and what does it represent in this context? Well, all I know is that it charges $25 per 1 hour. So that means that X is time, so we're going to have hours. And Y is going to represent the total amount of money we're going to spend. So that's the money. So at 0 hours, it's going to cost me $0. I haven't gotten the taxi yet. But it's going to be $25 for 1 hour. So 2 hours is going to cost me $50. Now let's say, guys, this one's a little different. I'm going to spend $100. How many hours is that? Well, if I'm $25 per hour, it'd be 25 for 1, 50 for 2, 75 for 3, and for 4 hours, it would cost $100. So then if I go up by two more hours, it's going to cost me $50 more. So therefore, 6 hours would cost $150. Now it says define your variables and write an equation that represents this situation. So the total amount of money is equal to $25 per hour, where Y represents the total cost and X represents hours. Now describe in words what the graph for the situation would look like. Well, it would be linear, it would be continuous, because you would, in a taxi, if it's $25 an hour, it's not $25 for the whole hour. It's not $25. Let me restate that. It's $25 for the entire hour, but you can be charged for a fraction of an hour. So if you stayed there for like 30 minutes, it would charge you $12.50. So it'd be linear and continuous. It would have a rate of change of 25, because that's what I'm going by each hour. Now explain how you know the situation is linear by using the context. And it's linear because of the rate of change. All linear relationships have a rate of change. And the rate of change is $25 per 1 hour. Now, if you only have $15 to spend, how many minutes can you ride in the taxi? Well, let's go and look at this. The total amount of money is $25 per hour. And you only have a total amount of money to spend of 15. So what this would look like is 15 is equal to 25x, and when I divide both sides by 25, this will give me x equals And both of those are divisible by 5 to get 3/5. Okay? Now it asks for minutes, but we're going to leave it in terms of hours. So 3/5 of an hour. And if you'd like to know how many minutes that is, um, well, if 5/5 is an hour, or 60 minutes, that means 1/5 of an hour is 12 minutes. So if 3/5 of an hour is how long we're staying, you'd be staying for 36 minutes. That's a tricky question, so let's just leave it as 3/5 of an hour, which is what I will accept. Now change the context. And that means every 25, I am charging this tax, this taxi charges $25 per hour. Let's go and look at another one now. Let's see, we got 2 more pages. Okay, perfect. So it says use the context. Your friends, our friends, go to the state fair. It costs $6 to go into the fair and $2 for each time you go on a ride. Relationship between the number of rides and the total cost. Well, we can control the amount of rides we go on, and the amount of rides is going to affect the total cost. So there's two things we need to take into account here. The $6 per ride and $2 for $6 to get in and $2 for each ride. So it says take the rate of change. Before we do that, let's make this a table. And we're always going to get charged $6 to get in. And it's going to cost me $2 per ride. And I'm going to go on 3 rides. 2 times 3 is 6. Costs me $6 to get in as well. So 4 rides would be, once again, $6 to get in, $2 per ride, and 4 rides. 2 times 4 is 8. 8 plus 6 is 14. And then finally, 6 plus dollars to get in, plus 2 times 5. 2 times 5 is 10, plus 6 is 16. Alright, now to set the rate of change. The rate of change is how much I'm increasing by a ride. So now the total cost per point, I'm increasing by. Every time I go on one additional ride, I am going to spend an additional $2. So the slope of the cost, remember, is always the change in y over change in x, or how much my total cost is changing over how much my total ride is changing. So for this instance, it was $2 for every one additional ride. Okay? So my slope is 2 over 1, and that represents the $2 per additional ride. Is this relationship proportional? Well, let's go ahead and look at my ratio of y over x. This is different. We're not looking at the change. We're not looking at the increase. We are just looking at the values of y over x. So this would be 12 over 3, which is 4. Then this is 14 over 4, which is 3.5. And then this is 16 over 5, which is 1, 2, 3 and 1/5. And when I look at these, you're like, oh, none of those numbers are proportional. And we would say, no, this is not proportional because it does not have a constant of proportionality. So make a graph and label the x. So what we're going to go over here is rides, and this is cost. And I know just to get into the park, it cost me $6. And then when I plug some of these values in, 3 rides cost 12. 4 rides cost 14. And 5 rides cost 16. And you can see that we can fill the other values. Now I want you to notice that this is 1, 2, 3, 4, 5 on the x-axis. And over here it would be 2, 4, 6, 8, 10. And you can see my rate of change by going up 2 over 1. Up 2 over 1, up 2 over 1. And some of us are thinking, wait, you're only going up 1 block. that up 2 over 1 if you're only going up 1 block. Because shown here, each block is worth. Okay, so let's state the coordinate of the y-intercept. And that is here. This is 6. It's 0, 6. And what that 0, 6 represents, that is 0 rides costs me $6 for the entrance fee. So it is going to cost you $6 just to go get into the park. Now define your variables and write an equation. All right, well, y is going to equal total cost, and x equals the amount of rides, and what this is saying then, the total cost is equal to $2 per ride plus $6 to get in. Your constant, no matter how many rides you go on, is going to be the $6 to get in. Now, where do we see the y-intercept in the equation? And we would say the y-intercept is always our constant. So the number with no variable, like the +2, the +7, the -4, that is going to be our y-intercept on a graph. So in this instance right here, my y-intercept is 6, so my equation will have a +6. Now suppose we have $25. So let's remember this. The total cost is equal to $2 per ride plus $6. And we only have $25. So, total cost is y, and I have total cost of 25. So let's see how many rides I go on. So if I have $25 and it is $2 per ride plus the $6 to get in, I can begin to solve this. So if I minus 6 on both sides of the equal sign, this will give me 19 is equal to 2x. And when I divide both sides by 2, I'm going to get x equals 9.5. Now think about this logically. Can we go on half a ride? And the answer is actually no. So we'd have to round this down to 9. So I could go on 9 rides. Now explain how this situation is linear by using the context. And so it's not saying because it has a rate of change. We know that it's linear, but it says by the context, so by the story. And the story tells us that it cost $2 per one ride. And that's what makes it linear. Now, how would you change the context so the relationship between the total cost and the number of rides is modeled by the equation y equals 2x? And what this is saying is there's no constant. There is no $6 fee to get in. So we'd say the fare is free to get in. But it is $2 per ride. All right. So now it says, how would you change the context so that the relationship between the total cost and the number of rides is modeled in y equals 6? I want you to realize, guys, the original equation was y equals 2x plus 6. And the 2x represent the $2 per ride. And now the $2 per ride is gone in this equation. So what am I left with? The $6 to get in. So the fare cost, $6 to get in, but all the rides are free. Okay, last one. Yep, last one. So it says complete the table. So Zigzag Bowl charges $4 per hour for bowling and $2 for shoe rental. Complete the table. State the rate of change here. Well, let's start with the table. So, the thing that we can control is the amount of games. And then the amount of games affects the total cost. So remember, it's always $2 for shoes, and it's $4 per game, and we played 2 games for a total of 10. So if we played 3 games, we still pay $2 for a pair of shoes, plus $4 per game, and it's $3 per game for a total of 14. One more time, $2 per game, plus $2 per shoe, plus $4 per game. Play 4 games for a total of $16. So it says state the rate of change. What am I going up per game? So the total cost increases by $2 per game. So total cost increases by $2 per game. Now, is the relationship proportional? Once again, I have 10 over 2. And I made a mistake right here, guys. It's not increasing by $2 per game. It's increasing by $4 per game. So it went from 10 to 14, 14 to 18. My apologies there. Okay, so now that we got that right, the total cost increases by $4 per game. So it'd be 10 over 2, 14 over 3, and 18 over 4. This reduces to 5. This reduces to, 3, 6, this is 4 and 2/3. And then this is 4 and 1/2. And as you can see, none of these values are the same. So therefore, this would be non-proportional. And the part in the context that makes it non-proportional is the cost of shoes. So next what we're going to do is we're going to make a graph where x-axis represents the total amount of games, and then the y-axis represents the total cost. So if it was $4 a game, if I have to pay, no matter what, $2 for a pair of shoes, and now I'm going to have to spend $4 per game. So that means I'm going to go up 4 per game. So up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1, so on and so forth. Now, if people are wondering, hey, how come you're going up only 2 and over 1 and saying up 4 over 1? The reason why is because, once again, each one of those blocks is worth 2. So 2, 4, 6, 8, 10, 12, so on and so forth. Okay, what is the y-intercept? The y-intercept is 2, and that represents the $2 for the cost of the shoes. $4 for the cost of the shoes. And now it wants us to define your variables and write an equation that represents the situation. So I'm going to have x represent the number of games, and y represents the total cost. So the total cost is equal to $4 per game plus the $2 per shoes. Where do you see the y-intercept in the equation? Well, the y-intercept was 2. And just like the previous example, the constant is always the y-intercept. So the constant is the y-intercept. And once again, I apologize. My iPad's acting slow. Having making my handwriting look a little funky. So if Janine has $15 to spend, how many games should she play? So she has $15, and it's $4 per game, plus $2 for shoes. So now I can go ahead and solve this. I'm going to start by minusing 2 on both sides. This would give me 13 is equal to 4x. And when I divide both sides by 4, I'm going to have 3 and 1/4. Now you can't play 3 and 1/4 games. They charge you by game. Therefore, you can only play 3 games. Explain how you know the situation is linear by the context. Well, the context has a rate of change of 4. And that represents the $4 per game. Alright, how do we change the context so that the relationship between the total cost and the number of hours is modeled this? In here, I have a rate of change of 3. So that means it's $3 per game. And this plus 5 would represent, and it costs $5 for shoe rentals. Okay, guys. That concludes our lesson. For any extra time you have out in class, go ahead and start your homework. Homework today is 2.1E, I believe, or the study guide. Please double check the calendar. And we will have a after-school review option in the Learning Commons.